Good morning from München. So my name is Caroline Lasorne. So I guess I add again to the diversity of the group here. I'm a numerical analyst, and I'm mostly concerned with time-dependent Schrödinger equations for molecular systems. So my idea now is to share my screen with you and to guide you, hopefully, to my blackboard. Do you now see my blackboard?
Yeah.
Perfect.
This is black and squares.
Perfect. This is what I wanted. So now I'm switching to tablet mode. I hope you're still with me. Okay.
Yeah.
Perfect.
Yes.
So then you will get, as far as I can manage, as close to a conventional blackboard presentation, just to slow down a bit and to have less slides in our life. Okay, so please interrupt, comment anytime. There might be technical or also other problems. Please just talk to me if things get wrong. I want to talk about separation of scales and quantum classical approximation. So this is the title of my talk. And the idea is that you get a guided tour of chapter 5 of a recent preprint, which is joint work with Irene Burghardt, Remy Karl from Rennes, Fermanian Kammerer from Paris, and Benjamin Lasorne from Montpellier. So you see, we are a French-German team of theoretical chemists and mathematicians of different flavors. The question we were addressing, we looked at the time-dependent Schrödinger equation in the presence of a small semi-classical parameter. And we looked at Hamiltonians, system bath type Hamiltonians, which single out an X part of the system, which has a governing Hamiltonian HX, a Y part of the system, and a coupling between the two parts, a coupling by a potential we call W of X and Y. The quantum part of the system, the HX, can be whatever it is. For the more classical part of the system, let's say the bath, we put a Schrödinger operator in semi-classical scaling. So we have a Laplacian with a small parameter in front and a potential that we call V2, arbitrary, but somehow nice. We need some smoothness for the estimates we are aiming at. So this is the time-dependent equation, and the initial data will have a separation form. So the wave function is a function of two coordinates, but the coordinates itself, X and Y, each might be multivariate. Dimension is not the issue here. We initially assume separation in the form that we have somebody in the X variable we call phi naught, and in the other variable, the Y, I denote him by G for Gaussian, but actually the Gaussian needn't be a Gaussian, it just needs to be a wave packet. So we put some normalizing factors, we put some amplitude, and we assume localization around some point Q0 at a scale of square root of epsilon in terms of kind of variance. And then we allow for oscillations, kind of a wave packet with a rather general amplitude. And the center, as I said, we have a position and a momentum center, let's say in R2D, and the amplitude function is working, is rather arbitrary. I mean, of course, it needs to be square integrable, and maybe you want to add some smoothness. If you think about a Gaussian amplitude, you are definitely on the safe side, but it needn't be Gaussian. It could be Gaussian times polynomial or whatever you would like. Okay, so what are the questions I would like to discuss in this short guided tour? So first question is, how accurate are product approximations? So I want to look at approximate wave functions of the form, of course, I mean, time dependent. We are talking a time dependent problem, and I want to evolve in the x coordinate something I call psi1, and I want to evolve something in the y coordinate I call psi2. And we want to ask the questions, how accurate are simple approximations of that type? Of course, I need to specify further how I really propagate the individual parts of the product. And another question that naturally arises, how do we measure accuracy? So this is kind of the idea now for the remaining 20-25 minutes or so to work in this setting and to give answers to these two questions. Okay, so the idea now for, maybe let's mark him. So we have the y part of the initial datum, and we want to evolve him in time in the situation where we have a semi-classical Schrödinger operator with a Laplacian and a potential, and recall that we have assumed this initial localization and in a phase space point P0, Q0. And of course, I mean, the first thing that comes to your mind that is natural in such a setup is to move such an initial wave packet along classical trajectories. So let me spell out the classical dynamics for the y part of the systems, and this will be absolutely no surprise. We use the natural classical equations of motion associated to a Schrödinger operator Laplacian plus potential. So q dot equal p, we will have p dot minus the gradient of the potential v2 along q. And to keep the phases right, we will also need an action integral, and the action obeys the usual equation of motion 1/2 p square minus the potential. And of course, we initialize the classical motion in the center of the initial wave packet. So Q at 0 will be Q naught, P at 0 will be P naught, and the action is initially 0. Okay, so and then we somehow could call the resulting approximation approach a collocation approximation. When we now work upwards from bringing these classical equations of motion into the y part of the system, while keeping in mind that we are interested in the effect of a coupled motion. We want to see coupling of scales, and we want to see the interplay between the x and the y part of the system. So the collocation approximation treats the quantum part, the first part, the x part, very generally. We just allow for the quantum motion to be what it is, and we add the coupling while collocating the coupling potential at the classical trajectory that we just defined. Initial datum is, of course, this general square integrable function we discussed before. Whereas for the second part, for the more classical part, we pre-describe a kind of an harmonic oscillator motion to build up a good amplitude for the wave packet. So I call the amplitude U2, and we perform a local quadratic approximation along the classical trajectory. So we get here a quadratic polynomial in y. We get the Hessian of the potential. We evaluate it, we collocate at the classical trajectory. So that would be the guiding Hamiltonian for the amplitude motion for the bath. And of course, we initialize with the amplitude of the initial wave packet. And then having these two constituents, we build, or maybe first I have given this amplitude. I build the wave packet for the bath. I keep this normalizing factor. I take my amplitude. This is now a function of t. I evaluate at a distance of square root of epsilon around the trajectory, and I move the oscillatory part with the classical frequency. And of course, I include the action, the classical action. And then at the end of the day, as already announced before, we build from all these building blocks an approximate wave function by simply multiplying the x component wave function with the y component of wave function. So yeah, I guess this is pretty clear. Maybe I revisit in blue the way the classical trajectories enter. So in the quantum part, they enter into the coupling potential. For the amplitude motion, we evaluate Hessian in the classical trajectory, and correspondingly the wave packet is built from all these classical quantities after the, let's say, the amplitude is built from this equation of motion. Okay, so that is what we refer to as a collocation approximation, because we enter in a pointwise fashion the natural classical dynamics. So what do we obtain for such a collocation approximation? So approximate, so accuracy.
Caroline,
yeah.
May I interrupt you a second? Just a question on, point 5.
Yes, please.
So in the equation for U2, you don't have feedback from W, from the interaction. Is it also part of the approximation?
No, you are perfectly right. As far as the classical part is concerned, there is no feedback. Yes.
Okay. Thanks.
You're perfectly right. It's just the classical, the classical trajectory in. Let's do it like that. Here, right? Here where it enters. And as you said, I mean, this is an extremely simple approximation, very simple in several respects. It's simple because we just go for product form. We don't go for a multi-configuration ansatz. We really do simple products, and we just allow the bath to act on the system. But as you see here in the build-up of the amplitude equation for the wave packet is purely built by classical equations of motion. Also there, it is really just the V2 that is present. It's an extremely simple setup.
Okay, thank you.
But surprisingly to us, when we started this joint project, we of course visited the literature, and our expectation that we would build on a lot of previous results, but actually we didn't find them. So at the end of our literature search, we agreed that it will be us to propose an analysis of the most simple approximation you can think of, and then to move on. Of course, I mean, I guess it's just fair to say that I'm still a bit nervous that somebody will tell me, but look, this has been proved already by someone before, and you're redoing things that are already known. But at least in the literature we looked for, and in the language we speak, we didn't find that kind of explorations. So accuracy in norm. What can we say? So we fix a time horizon, capital T, and then we find a constant, and this constant is kind of our litter bin. Where all the things we are not so interested in enter. So on that fixed time horizon, we compare the true wave function with the approximate one. We have built, and then there's of course this overall constant, linear time dependence. And the interesting thing is that we see our small semiclassical parameter coming up together with something we measured now, the coupling strength, as the y derivative of the coupling potential. You could do different, let's say, different ways of measuring the coupling, and we have done that. But what is kind of, let's say, interesting to note, so we have, this is kind of there's the effect. Let's say we have the effect of semiclassical approximation, wave packet approximation. And maybe I should stress at that point that we do not do a WKB, we really do a global and time valid wave packet approximation, no caustics, nothing present once we have set up the classical equations of motion. It's kind of canonical to build the wave packet by looking at this time-dependent harmonic oscillator and then to systematically build the wave packet like that. And kind of the thing we are most interested in, this is kind of the effect of the coupling. And at the level of this norm estimate, you might be tempted to say that somehow the strength of the coupling and the classicality of the bath have to be in an appropriate ratio. So preferably the coupling has to be smaller than the epsilon, such that you get a meaningful approximation when you proceed as simply as we just did. So let's look at another accuracy measure. So let's somehow assess the accuracy of this simple approximation in terms of observables. And as for observables, of course, I mean, various flavors are possible. For now, let's say in terms of observables in Y. So I want to look at an operator op of B that is acting on functions in Y. And now I do Y quantization of a phase space function. Phase space now thought in terms of the Y part of the system. So I have Y plus Y prime, some momentum xi. I have to do the Fourier transform in the difference, and so f of Y prime, this is integrated with respect to xi, so I have the kernel of the Y quantized operator, and I close the action, and for consistent scaling in epsilon, I need this 2 pi epsilon d. So let's say this is defines an operator acting on the Y degrees of freedom, and we use epsilon scaled Y quantization, which gives us a fairly general and nice class of observables. And the kind of, and now we ask ourselves, how do, if we use this observables, and when we build expectation values for such observables, how do they compare kind of the true expectation values versus the approximate one we obtain from cooking up our approximate solution in this product Y? So then we compare, let's say, the true expectation value, it's let's write it psi of t, so inner product operator psi with the one induced by the approximate wave function. So just to recall, the approximate is built from the product, where the coupling on the quantum part is merely through the collocation of the coupling potential, whereas the classical part is a semi-classical wave packet approximation. So what do we get? So again, we set a time horizon. So for all time t and functions b, there exists, and again, I open up my liter bin, now I call it k. And when I now compare on the time horizon the true expectation value with the approximate one, then we get an estimate that is slightly different from the previous one when we were looking at the norm. Same thing, liter bin, linear growth in time, since we are working on a finite time horizon. And now it looks like that the interesting part is plainly multiplied by square root of epsilon. So we get a much more kind of pleasing situation in terms of accuracy when you compare back. Here we had this fraction where we kind of thought coupling has to be small compared to the semi-classical scale parameter epsilon, whereas here I just have to look back for the color coding. So coupling, if coupling is small, then we get a small contribution here. And if the parameter epsilon is small, we get a small contribution here. So the situation is somehow more alleviated, and kind of this better estimate is due to the averaging in Y caused by, let's say, RB and kind of, yeah, and taking the inner product. So when you look at the observables, the estimates are better due to this induced averaging, and kind of course, I mean, you still get the message, the semi-classical scale and the coupling should be small in order to have a meaningful estimate. But then at the end of the day, you would somehow say, okay, if both of them are small, and then it's the largest of the two that actually dictates. So we could conclude and say what we see, we estimate the sum by twice the maximum of semi-classical parameter and coupling strength. Whereas above, when we were looking at the norm estimate, we clearly came to have a meaningful estimate. The coupling needed to be smaller than square root of epsilon. And on top of it, for the norm estimate, square root of epsilon is the guiding quantity, whereas for the expectation value, it's a plain epsilon. Okay, so when you have this type of result where you see a kind of, you could phrase the slogan averaging helps, you might have the idea of also improving the rigid collocation approach by something that is more mean field in nature. So this would now be, I guess, number 8. So a mean field approximation in the following sense. So we would alter our equation of motions for the approximate solution, not drastically, but slightly. And instead of having the coupling potential evaluated in a classical trajectory, we might think that things get better when we put an averaging with respect to the classical part of the system. So where, for example, this average here in the y coordinate is performed like integral of the full function, and then we integrate with respect to the second part of the system, and just, I mean, if it is normalized, the following thing is just a 1, but to see the scaling, right? So that would be one other choice here. And the amplitude, kind of to have it in balance, would also be built from a harmonic oscillator, where the information from the Hessian of the potential would be included via averaging over the full solution. So this is in spirit a bit like the time-dependent variational Gaussian wave packets that have been introduced by Coulson and Karl Plus. These are similar equations of motion. You have for them, you average across along wave packets. Okay, and then kind of the let's see, I still have maybe a bit of time, so that would be the setting up of the mean field approximation, and of course also the underlying classics would be mean field trajectories. So we would have, let's say, of course, for Q there is nothing to average, but for momentum we would average again the gradient of the potential, right? So etc. Same for the action. So surprisingly, so let's say 10, same error estimates. Up to differences in the constants. Let's say in the litter bin constants, so not the relevant one. For the collocation, and the mean field approximation. Again, kind of both times observable estimates are better than the norm ones, the norm estimates. So this is kind of our current conclusion, that at the level of analysis we have conducted, we do not see a beneficial effect of the mean field averaging. So what is currently happening? So let's say conclusion. So we currently have an ongoing numerical investigation on a concrete on a system bath Hamiltonian with cubic coupling. So we want to learn how sharp our analytical estimates really are. And second, we have also started to think about lifting the analysis to sums of products. And of course, I mean, just taking up Frederica's question or comment, more elaborate coupling would be interesting, but I have to confess that this is at the moment just a thought and not nothing that has been already worked on. And of course, I'm very interested in more comments and questions. So I'm now bringing back my Blackboard to the computer. I'm trying to stop screen sharing, and now I should be back. Yes. Okay. Thank you for your attention.
Thank you very much. So time for questions now. Plenty of time.
I was too quick.
No.
Good.
You started 5 minutes late, so we have 5 more minutes to questions. Yeah. Isaac.
Hi. Thank you very much for the talk. It was very nice. So would I be right in saying that your kind of, or your classical states that you're considering are kind of like a generalization of coherent states? So like, yes, you set up some wave packet, and so then your conclusion is that you can't maintain a kind of product state between your coherent state, which I guess is being used to control your classical system. Like they don't remain in a product state for all time.
So maybe I start sharing my, now since I don't have to write anymore, I think now you see my Blackboard again, right?
Yeah.
So maybe let's go up to hopefully pick, as you correctly said here, so when we look, let's take maybe another color. So when we look here, you see the build-up of the coherent state, right?
Right.
And then, as far as the approximation is concerned, it enters here, right? So the approximate wave function is built by a quantum part. The quantum part just feels the classical part via this collocation in or mean field averaging, as I just explained later, of the coupling potential, and the coherent state goes as it wants to go. But I wouldn't speak of somehow of a breakdown, because we have error estimates that tend to 0 once relevant parameters are set to 0. So here for the norm estimates, you see when coupling goes to 0 faster than epsilon, then things are fine, then square root of epsilon. And on the level of the observables, you even see less strict conditions, namely coupling and semi-classical parameter have to tend to 0, and then you're fine. So it's kind of, we are trying to quantify both effects, the effect of the coupling and the effect of the classical approximation.
Right, I see. And what's the nature of the coupling? Just depends on the position of the.
So a priori, the Hamiltonian comes as it comes, right?
Right. Yeah. Yeah.
And in some sense, hopeful. I mean, the idea was, of course, of the analysis to shed a bit more light on what are the relevant sizes in a system that make such a simple approximation meaningful, right? And when you now look here, you somehow see, okay, something like a derivative in the coupling direction has to be small. And of course, the bath has to behave somehow classically as measured by the epsilon. Right. This is at the kind of at the current level of the investigation, our conclusions.
Okay, yeah, cool. So I guess somehow I might expect that if the coupling was dependent on if it was depending on the momentum of this classical state as well.
Yeah, then you could do up. I mean, this was okay. So the theoretical tools we are using would be stable and would allow more general forms of coupling. But I mean, you see, we are an interdisciplinary team, and I think part of that work was also to agree on a common language and to do things together. I think here the coupling could also be done differently, but of course, and then the theoretical tools we used would accommodate for that, but at an increased, you have to write more formulas.
Right. Yeah. Okay.
And
cool.
We wanted to keep the thing in a way that all of us feel healthy.
Yeah, that makes. I mean, it's a natural coupling, I guess.
It's a natural coupling, but you're right on that point. You could elaborate, and the tools we have used would survive, would do it.
Okay, great. Thank you very much.
Are there some more questions? I don't see any questions. Yeah, I see one. Please go ahead.
Yeah, maybe following up from Isaac's questions, I guess if this coupling is, if the system is chaotic, does that make any difference in terms of when the kind of classicality or when the coherent state approximation breaks down? Does that make a difference?
Sorry, could you say it again?
If the system is chaotic, like if the coupling leads to some does that make a difference in terms of how quickly the approximation of treating this as a Gaussian?
I see. So you're asking about my litter bins, right? Mm-hmm. So what you are asking is, where does the nature of the classical dynamic enter into the estimates?
Yeah,
and it enters actually here, because I have said I'm working on a finite time horizon, and then kind of couple of derivatives related to the classical dynamics are then just bounded by some constant, and that enters into this collective C here. And downstairs for the observable, it's the same mechanism. But actually, if you have, I mean, the worst thing that can happen for this type of estimate here would be the situation where the classical part is a bottom-down harmonic oscillator. This is the situation where the corresponding quantities that have to be estimated grow exponentially in time. The other regime that you indicated, a chaotic classical motion, is actually not so bad. as this thing where you have somebody flowing down a parabolic hill. So it's kind of an intermediate thread. And at the moment, everything is in, I mean, I presented you a version where I put up this finite time horizon litter bin, but we have in the paper also more refined estimates where we open the time horizon. And of course, in the worst case, you can have exponential growth of the constant with respect to time once the underlying classical dynamics is bad. And bad in terms of large Lyapunov exponents. Does that answer your question somehow? I think it was Jonathan, right?
Yeah, that's right.
That
does answer the question.
Okay.
Thanks.
I don't see other questions. So thank you very much. We meet again in 25 minutes.
Ah, good.
Hi, I'm sorry, my laptop crashed exactly during the discussion session. I wanted to ask about the linear growth. I think you mentioned this in Jonathan's question. My question was whether this linear growth estimate is tight, or is there some hope that maybe some averaging effect leads to maybe a slower discrepancy?
So do you now see my blackboard again? No? I have to look. No, it should work. So you have the blackboard again?
Yes.
Good.
Yes. Yes.
Yeah. So as I just discussed, so here, the constant I put up depends on the finite time horizon, and everything kind of when you start making things explicit in terms of dependence of time, really here, I mean, then the worst thing that can happen is exponential growth. And exponential growth is kind of belongs to the situation with Lyapunov exponents with, I mean, however you phrase it at the end, you get something like exponential to the Lyapunov exponent times time. So this is actually possible and might happen, which comes together with a lousy coherent state approximation of the Y motion.
Sorry, but this is something that I didn't quite get. Maybe I missed something in the talk. So in the formula you're presenting here, C has still some dependence on the window. So 0
exactly.
to T.
Exactly.
I see.
So exactly. So the constant here is really a constant that depends on the finite time horizon. And once you start lifting this type of constraint,
yes,
and if you don't exclude situations like a downward tilted harmonic oscillator, then you inevitably have exponential growth with respect to time of the constant.
I see. And if I would like to use your estimates and maybe target some global epsilon to say maybe my approximation is at least this good, then this curly epsilon and the interaction strength would in principle have to be exponentially small in this capital T time scale.
Yeah, exactly. And this is, of course, I mean, a race you cannot win. If you have exponential growth with respect to time,
yes,
then it's pretty clear that that you can't win. because as kind of as small as your coupling and as small as your semiclassical parameter are, you will be quickly in the regime where the exponential growth overtakes, and then it's definitely a bad idea to go for this type of approximation. So for the numerical exploration that is currently underway, we have a system with a cubic system bath coupling, and it indicates that kind of we have a quartic oscillator in the y direction, and we couple with another one, and it looks like something like two oscillations between the well are fine, and then at some point this simple product approximation is losing track of what's going on. And this was kind of also the motivation here of saying that we are actually targeting now multi-configuration ansatz functions, and I guess in Irene's talk you will have plenty of them, but of course the amount of mathematical control we have on the simple objects, the simple products, we are not yet there that we can control a glorious multi-configuration function like Irene is using them routinely. But we are working towards that. So this is our ambitious next goal.